right, everybody. Good morning to America. Good evening, afternoon to Europe. Very happy to be here this morning with Giovanni, bright and early from the West Coast. Thank you for joining, Gio. Good morning. Happy Easter. And yeah, let's get right into it. You've been busy. First of all, the Scientific Bitcoin Institute. I noticed this. Congratulations. I would love to learn more about it. I don't know, just briefly. Any
So
anything you could tell us?
it is a non-profit. It was incorporated sometime in November, I think, last year. And it's in the United States, but the scope is very global. We will try to have a presence everywhere in the world, different branches. Right now, we have actually a physical location in Italy, in the city of Torino. This company that is one of our sponsors is called Folger. They are building this hub, like it's a 4 or 5 stories building in the middle of a major city in Italy, Turin. In fact, in one of the main squares. The main floor is going to be on the square itself, where there'll be a huge big sign, a Bitcoin sign, so people can watch it from outside. They can come in and have an experience about Bitcoin, learning about what Bitcoin is. The end of this experience will be actually buying a small coffee using Bitcoin. We are in Italy after all. And
Of course.
I don't remember where it is, but maybe third floor, there is an amazing view. Actually, some of the nicest buildings are like historical banks. So it's kind of interesting and almost symbolic. And that is actually the location. One of these offices is the location for the Bitcoin Institute, our physical location. It's a large office. We will have several computers. Students can come in. There will be some mentoring operations. Like there is a major technical university, the Polytechnic of Torino, and we're already collaborating with them. We're having discussions how to study Bitcoin. We have in the math department, we have a cryptography group that is interested in studying Bitcoin. But it's not just going to be cryptography. It's going to be many different topics of it, including the power law. So we want to understand more about the power law. We want to do data analysis, verify, because up to now, has been mostly here on X, right? People like me, like you, doing models, trying to use our mathematical knowledge to make sense of it. But it will be nice to see what the scientific community in general thinks about. So that is one of the goal of the institute, to actually develop this relationship with the academic world. So many different professors, in physics, mathematics, economics, then involve also graduate students, so maybe doing some PhD thesis on these topics, and anything that is related to Bitcoin. It doesn't have to be the power law. It could be different topics that have to do with the economy, sociology, maybe the energy consumption in the network. So the idea is that our vision is that Bitcoin is not an asset, is more like an experiment. Like humanity is doing this experiment where many different, let's say, interest or different type of technologies are tested, or different interactions between people, so involving physics, involving economics, anything with even history, monetary policies. So if anybody has a particular angle that wants to use to study Bitcoin, but in a serious manner, looking at publish papers, books, references, and he wants to write a paper, a book, etc. The institute is interested in connecting with these people, but also providing funds. Right now we are starting with a pretty good budget. It's not something that we are doing in a garage. We have right now almost like $1 million budget. Our first year, so it's pretty ambitious project. And so we are going to provide funds, scholarships, um, having servers, to analyze the on-chain data, and so many different activity of this type. Yeah.
Great. Let's excellent. I'm not too far from a Milan flight.
Yes.
No direct, I think, to Torino.
Yeah.
But it's a beautiful city there in the foothills of the
Exactly.
Italian Alps, and I've been there many times. And the
ATP you're
finals,
welcome.
ATP finals are there as well.
Come and visit. In fact,
I would love to.
On May 7, I don't know if you are around. Where are you located right now?
In Latvia.
Where?
Latvia.
I didn't understand.
In Lithuania.
Okay. Yeah. So it's not impossible, right, to come to Italy. It's a relatively short flight. We're going to have a big event. May 7 is going to be the inauguration of this hub. So there will be a big party, there will be press, So if you have actually an opportunity and you want to come to Torino, you're more than welcome.
Thank you.
Yeah,
I will
be
see
there
if
myself.
see if I can make it work out.
Yep.
Yeah. Great. Okay. Well, congratulations on that. I look
you.
forward to what you guys are doing and learning more, maybe contributing if I can.
Yeah.
So let's move right into it. You have had so many nice hits here recently. I want to start with the eigenmode.
Yeah.
And the cycles and your conclusion. Basically, it's very tight around the 4-year idea. So yeah, why don't you just explain it? I mean, I can put it up on the screen if you want, or you can, your tweet.
Yeah, go ahead. You can show the particular tweet. Yeah, I have other slides.
Okay.
I don't have the particular one, but we can discuss.
Yeah. Go ahead and tell us a little bit about it. I'll put it up in just a second.
So I'm looking at, that me and Stephen Perrineau have this show that is called The Physics of Bitcoin, that is also the title of my book that we can discuss also in a moment. And in the show, we always try to find new ways of understanding Bitcoin. Basically, almost on a weekly basis, we find new results, new ideas, And so we're exploring all possible manners of describing the data. And so this is something that is very typical in physics, this idea of eigenvectors, right? So basically is a way of breaking down the data in terms of components. Like, just to give you an idea, it comes from some idea from geometry. For example, imagine you have a vector, right? So I have an airplane flying, and I want to determine the position of an airplane, right? I will need 3 coordinates. I will need latitude, longitude, but then altitude, right? So these 3 components form what is a vector. So you can imagine, I don't know, maybe you need a point of reference. Let's say maybe it's the airport from where the airplane started the flight. I don't know, it could be New York or whatever. And then you are describing the distance, the total distance of the airplane from the airport. And in physics, we describe it like a vector, right? Like a big, huge arrow. And then this arrow is going to have 3 components, right? It's going to have an X, Y, and Z component. And these components are perpendicular. That means they are orthogonal, so they don't have anything to do with each other. They measure things that are 90 degrees from each other. Now, in geometry, this is easy to understand, right? X, Y, and Z direction. But it's an analogy to describe what you can do uh, in describing data in general. Right? So basically, we are trying to
Yep.
find some kind of components of a data that are independent from each other. And there are different techniques of doing this. It's basically the same thing. You're trying to look at the data, you decompose it, and then you're trying to find through some relatively sophisticated techniques um, what are the main pieces of data that make up what you're observing. And so in a time series, that is what Bitcoin price is, mainly will be, is there some kind of general trend, right? That will be, if that general trend is dominant, that we call it the main eigenmode, you know. That will be the dominant eigenmode, will be where most of the data is. And guess what? When we do this decomposition, and this graph doesn't show it, maybe, I don't know if you can go back to some of my, I don't know if I have another post where I show, I have some slides that I could pull out, but uh, if you decompose this blue line in its mode, the main mode is actually the power law itself. Maybe it's in that slide. Yes. You see this straight line that you're seeing there? That is the
Yep.
power law. It's very, very close to be the power law. That is the main mode. So it's basically it's finding with a completely different technique that is what we usually we use, right? Or yourself you are using this regression line. Regression line, you plot the data in log. Um, then the data looks linearized. You're fitting a line and saying, well, okay, the data looks linearized. A line in a log should be a power law. Just go through some simple algebra to demonstrate that. You
Yep.
measure the R square that tells you the goodness of it. You measure the slope that tells you the power of a power law. The beauty of this method that you're not telling what to look for. It doesn't know. It doesn't understand. You're not telling it fitted with a line in a log graph. It is looking by itself for what it thinks are the fundamental components of the data. And the first thing he finds, and by the way, it turns out that is kind of close to 97% of the data. 97% of the data is explained by the equivalent of the power law. And it's a completely model independent approach. So it doesn't, you're not going to ask, because that is one of the criticisms that many people have with the power law. They say, well, you are assuming from the start you're looking for a power law. It's not really a good criticism because not many people found the power law, right? We were
Right.
among the first ones. You have to
Right.
have that intuition that the data doesn't look exponential, so maybe something else. And for physicists, it's easy to plot things in a log plot because we do all the time. The data looks linearized, but there is a little bit of assumption. You're saying, oh, all that oscillation around the straight line are not important. The straight line is what matters. You are doing it manually. This is a completely automated method to decompose the data in all these components. And so, of course, it's going to find the power law and is assigning some weight to that. And the weight is 97%. And then whatever is left, it's a different language in the regression language, we will call them residuals, right? You
Mm-hmm.
subtract the long-term trajectory, and then whatever is left over are the residual, and they look like oscillations, right? When you do that. Well, again, this method, it is extracting these oscillatory modes by itself. And again, it's assigning weight, right? Say, okay, there is this first oscillatory mode. It turns out that is something that looks kind of like the 4-year cycle, and then it adds more stuff until basically you reproduce. And in fact, if you go back to the picture that you were showing, is reproducing the entire pattern, right? It's very, very, you can see underneath there is in gray, there is the real data of Bitcoin, and it's a very, very close reproduction of that, right? And it takes, like I say, 97% comes from the power law, and then by adding few of these modes, you can reproduce the cycles. So yeah, it's a very interesting book.
This line here,
Yep.
this is the SSA trend.
Right.
This looks kind of exponential, no?
No. It's the power law. It's actually the power law.
But the x-axis is linear in this, and it looks like a straight line.
Yeah, it's log linear. It's not quite a straight line.
Yeah.
It's not quite a straight line.
I guess it's probably just the compression of the y-axis, but the red line just to me seemed kind of straight.
It's a power law, and it's this mode also depends on how much data you're feeding, right? So, for example, it's much more clear if you're breaking it down a little bit, because here we are dividing the data by 4 year amounts, but it's kind of almost indistinguishable from the power law when you plot it. If you plot the power law on top, in particular the last part of the graph, it converges to the power law. So it deviates a little bit because it doesn't have enough data initially. So it's trying to do all this calculation. It doesn't have enough data, but then little by little, it converges. I have much better pictures where you can see it's basically finding the power law. It converges to the power law. That mode converges to the power law.
And the bottom line is it finds something like a cycle at 4.19 years without knowing about the halvings.
Exactly. You say,
which is pretty remarkable.
I see this oscillation. It's one of a possible mode. And then when you put it together, you are actually reproducing this. Now, this is not quite for years, right? It says, well, one of it's almost like I said, it finds ingredients, right? Say, to get this oscillation, one of the ingredients, one of the things I need to add to the recipe, it's a 4-year oscillation. But evidently, there is more to it, because you see, for example, the first peak that you're observing, it's only 2 years from the next one. And it includes that, right? So it cannot be just, so these are modes. Like, for example, 2 is alpha 4, right? So it's you will call it a subharmonic. So it's the real oscillations are more complicated. It's not just 4 years. There are all these subharmonics. Now, the picture becomes even more interesting when you are actually systematically try to find these peaks using other methods, like, for example, what me and Steven have, because these are all complementary.
I was just going to ask you. You guys have this other idea, this subharmonic, where 2027 could be a major top, correct?
Right. So the idea is that, and these actually,
you want me to pull that up?
Yeah. In fact, I will share you. So this method, I would say, the main things that you get from this method, and eventually we want to write a paper on this, because this is another thing that we are doing with Steven and the Institute. We are starting to write all these very systematic papers on these ideas. In fact, we just published on a preprint, and I send it to a journal. I don't know if you saw it. Otherwise, I will send you a copy. We just published the first systematic paper on the power law in general, right?
I can put the link up to that. Yeah.
And that paper had 7,000 downloads. It is really weird for a scientific paper. It's very unusual.
That's fantastic.
Yeah, I will send you a copy, and you can look at it, or maybe you can repost it on your.
I'll repost. It's I had all these links up, and then I shut that window. In any event, go back to the. We'll come back to the paper, but go back to the harmonics.
The SSA method, this eigenmode method, I think it gives us I think the most interesting component is that it finds the power law, and you say, I see the power law. I see the power law. You didn't tell me to look at, but it's there. It's impossible to the night, right? And then,
Right.
yeah, this is the paper that I was
That's the
describing.
paper.
And then now, it sees all these oscillations. You say, of course, there are also oscillations, and we need to characterize. That is not really the best way to characterize this oscillation. I think this other idea, and I will try to find the slides for this. And I really love this idea because it kind of, if it is true, it really is going to make everything so cool. And there is a little math behind it, right? Now, I got inspired by this physicist. His name is Sornet, and he's famous because he's a geologist, and he studied oscillatory phenomena, in particular associated with earthquakes, right? So an earthquake, you have this accumulation of energy in some location, and then stress is building up, and something breaks, right? Something in the structure of the earth, and then you have a chunk of the earth that is going to oscillate, right? And this is how you create these seismic waves, right? The earthquakes. And he got a lot of data, and one of the early grays in this field is trying to find a way of predicting the earthquake in advance, right? Because it's been an interesting scientific phenomena. Will have a lot of practical application. You can save a lot of lives, right? If you can alert people that there will be a big earthquake in some location. And one of the things he noticed was that just before an earthquake, the oscillations became faster and faster and faster. So he calls them log periodic because what happens? So imagine I have this oscillation, right? They became faster and faster. So basically the distance between the peak becomes shorter and shorter, right? If I do a drawing of this oscillation. Now, if I draw this oscillation in a log chart, that we are used to this idea with the power law, right? At least the people that have listened to my talks, or maybe you don't often plot it in a log plot. I do that. I plot the power law in a log plot, and people, they know what I'm talking
I'm
about.
getting some better charts up to do that, but
I
yeah,
know
I don't do it often.
we it looks like a straight line, right? Instead of
Yeah.
looking like a curve, like it do. Usually we plot it. If you just take the log of the y-axis, if you do the log of a power law, it looks like a straight line. Now, if you do the log of the log of time of these log periodic oscillations, instead of looking like they are squeezing, they are becoming faster and faster. So the distance between the peak becomes shorter. All of a sudden, they look periodic. So you are stretching them out, right? So there is some kind of weird transformation where something that looks curved look like a straight line. If you take the log of time, something that looks compressed, if you do it in a log of time, it looks kind of self-similar, right? It is the entire idea of power laws, because power laws, the property of power laws is that they are self-similar. Like you take a straight line, you take a chunk of a straight line, it looks
Yep.
like itself. That is one of the big deals, and this is why you need a physicist to discuss these things, because we train us to understand this, what is fundamental about power law. Power law is not just another curve. It has very fundamental property, and this fundamental property tell us something about the system, the nature of the system, the mechanism. So with these log oscillations, is basically something that didn't look self-similar. A sine wave is self-similar, right? But it's in chunk, right? Instead of being at any point, it's in this periodic oscillation, right? One periodic oscillation looks like another periodic oscillation, looks another periodic oscillation. In this case, but it will be a constant type of self-similarity. It's not very interesting. With a log periodic, you have all the scale, because you have oscillation at all scales, like slow oscillation, fast oscillation, even faster oscillation. And all these oscillations look like themselves, but at different scales, right? And we call this scale invariant. The difference between the scaling variance of a straight line power law, a normal power law, and this log periodic scaling variance is that it's discrete. It comes in chunks. So it's called a discrete scaling variance. But guess what? Both of them are power laws. And I
Yeah.
know that it doesn't look like that an oscillation is a power law, but it is. The trick is instead of having an exponent that is a real number, you make the exponent a complex number. And this is what this equation is trying to show. So me and Steven, and I actually added this model long time ago, all the way to 2014, when I started to see the oscillations in Bitcoin, the first peak and then the second, because I was familiar with the work of Sornet, because eventually he went from seismology to the financial market. He has an entire book that is called Why the Stock Market Crash, because he used this technique to actually predict market crashes, market bubbles. So he was able to predict several of them. He even made money with them, and he took the knowledge of physics and he applied to the market. And so, and the way you predict these crashes, because so first of all, say this is one of the things that physicists do. We've tried to find similarities between things that they seem very completely different, right? What an earthquake has anything to do with the financial market? It's this kind of a faster and faster oscillation that he observed in the earthquakes when he actually started to look at other things like NASA. He worked for NASA for some time because we were looking at cracks in material, and they behave in a very similar fashion. They start to oscillate before a crack, they crack, and they go this vibration in the material um, go faster and faster and faster, and then finally it's so fast that cannot be sustained, and the material cracks. Right. Same thing with the stock market. Just before a crash, the activity in the stock market, they will go faster and faster and faster. There is basically some kind of herding behavior. People are, it's almost like a feeding frenzy, right? So you see buying and selling, buying and selling. It goes faster and faster and faster. And you can extrapolate it to the point, right? If if you can fit the function that you're observing, you can extrapolate it to the point where the oscillations are so fast that are unsustainable. And so it's kind of actually almost a predictive tool where you say, oh, I see this very, very fast oscillation. It should be some kind of event in a couple of days from now. And it's so cool because I knew about them. I didn't apply directly. And I started to study Bitcoin. I should do it eventually we will have like actually an observatory, right, from the Institute where we can post these observation applied to Bitcoin for these faster and faster oscillations. And I did it one time while I was in some kind of X space. Everybody was up talking about Ripple and apply these equations to Ripple, and they say, "Hey guys, I'm seeing some crash happening very soon in Ripple," and everybody was laughing. Sure, of course, right? Now you're like a kind of psychic. You can tell that, and with such level of precision. And that evening, while I was going to sleep, there was a crash. It was really cool seeing it in real time. But so, what is the application of that to this? So, I was familiar with this idea, and when I saw this oscillation in Bitcoin, I thought maybe there is something similar, right? And I started to apply this equation to the bubbles, and then eventually I left this idea because I have to be honest, I got influenced by stock to flow. And he was talking about the halving and all kind of stuff like that. And I thought maybe this idea that the bubbles are log periodic is wrong. Maybe I should modify, because that is part of doing science. You get new data, you're trying to, not to impose your idea on reality, but a learning reality, right? And
Yeah.
so if you ignore the first bubble, then the subsequent ones kind of look periodic, right? Um, and so I abandoned that idea. And then now that we didn't see much of a bubble this particular cycle. Actually, Steven went back to it, or he rediscovered it, right? Because these are things that if you study enough, eventually you rediscover. And he brought it back and he said, hey, Steven, by the way, I was playing with these a long time ago, and now both of us are working together. But basically, the main difference will be that while before a crash, locally, you see a power law. That is what happens. In fact, even in Bitcoin itself, you go very close to one of the Sornet even wrote a paper on the bubbles in Bitcoin, and you see this local power law. It's not like the global power law that we observe. And then the oscillation became faster and faster. In our case, we see, if you look at the overall behavior of Bitcoin, you see this very long-term power law. And on top, you see this log periodic oscillation that instead of becoming faster and faster, they're becoming slower and slower. It's the same math, but with a different sign. Okay.
Yep.
And now, if you combine the two, the cool thing is that now you can write one single equation that looks something like this. It looks like some constant, then t, this is supposed to be an exponent, right? It doesn't look like an exponent, but it's an exponent. Beta,
Okay.
that is our usual 5.8, with
Slope.
the
Yeah.
slope, with
Scaling
almost like
constant.
6. And then I, that is, if you remember from high school, it's the imaginary number. So it's really weird to think that you can have an exponent that is imaginary, but it is. And so if you're combining both, right, you have the slope, of the power law, plus I, that makes these things oscillatory. I explained the algebra here. I share these slides. People can go a
Yeah,
little
yeah. We
bit
don't
of
have
the
to. We
right.
don't have
We
to
don't
do
have
that
to
here.
do that, but it's easy to demonstrate that if you have this imaginary component, then the math leads you to oscillations, sine and cosine. And this
Turn it into
omega
sine and
is
cosine.
the
Yeah.
main frequency of the oscillation. It is about 2. What does it mean? Because it's not going to be a periodic oscillation, is going to be a log periodic oscillation. You see, there is a log of time. Here, normally, if this was a normal sine or cosine, you will have only time. But instead, if you go through the math, you get a log. And so that is really cool, because then if this model is correct, and we can check if it is correct from the data, then one single power law describes both the slope of a power law and the oscillation. And now something like that looks like. I can show you how it looks like. I have other slides to show you that. And I think is super cool. So how will you do that? Huh? Um, Let me show you here. Okay.
Go ahead and share it again.
Yeah. So the first thing you do, you try to find this frequency, right? And this is called a spectrum. But spectrum means there is a technique in mathematics where you're working in this space, right? Instead of having time, you have frequencies. And then you apply this math to the data, and it's going to give you spikes if there is some particular oscillatory pattern in the data. This technique is called Fourier analysis. In fact, here I tried 3 different methods. I tried the Fourier analysis. I tried this method that is called Lomb-Scargol, and then brute force, right? So 3 different ones. The main difference is that instead of having just normal frequency, I have a log of a frequency, right? So I'm working this kind of a little bit weird space where I have frequencies on my x-axis, then I take in the log of these frequencies, right? These are these angular frequencies here. In fact, actually, this is another method. No, actually, sorry, this last slides puts these 3 different methods together. superimpose them. But you see this huge big peak that we observe, right? This is the main frequency that we are
Mm-hmm.
observing, and then it seems that there is a tendency for two times, not quite, and this could be disturbances. One theory could be that there is some inner frequencies inside how Bitcoin works. Then Bitcoins interact with the external world, like the market cycles, microeconomic cycles, whatever. And these frequencies are shifted a little bit, they are interfered. But this main frequency is so dominant that is almost nothing changes, right? And three different methods found it. And it's the value of this one is around, this it's around 8, right? um, and, and because it's 2 pi times 2, so it's close to 8. 2 pi is what is called angular frequency, right? It's you take the frequency and multiply by 2 pi because 2 pi represents a rotation. So, but basically, the main idea is that there is a mathematical method to extract periodicity from the data, and there is something very, very dominant. That something dominant, if you don't think in terms of log periodicity, you will think it's a 4-year cycle, but it's not. It's just that it starts with 2, then it goes to 4. It takes some time. In fact, probably we were confused by that as Bitcoiners say, oh, it looks like Bitcoin is oscillating every 4 years. No, it started with a 2-year oscillation. It went to 4. It extended and stretched it a little bit, and it still look like 4 because there are some subharmonic that are higher frequency. So what is now what is tending to become 8, now it becomes 4. You see, if this is going to double itself in frequency, it means that actually the uh, half of that, so 4. And and so it's like an illusion that there is a 4-year cycle. It was a gain, and now it's not going to be there anymore. In fact, it looks like this.
Let
If you, yeah,
yeah,
go
let
ahead.
me stop you there.
Yeah,
Do you have one that we can blow up just of that over the entire life of Bitcoin so far, from the 2 to the 4, the different harmonics? I know I
yes,
saw
yes,
it on Steven's page at
yeah.
some
Here,
point.
here it is. You see this graph, right? So if I show
Yeah, let me
that,
see if I can
so I go from the spectrum, that is
blow it
how we
up.
found these
But
guys, to actually how these oscillations look like, right? If you need to add not just the main oscillation, but like the other smaller peaks, because they are relatively strong too. And now you start to see the picture. Look at this, right? You see how complicated these oscillations look like. But basically, it's nothing else, right? There is some structure with this smaller peak, this peak, and this other one. Now, this one is being repeated again, but now you see how it's getting stretched, right? So,
I do.
yeah, this here is getting stretched and then stretch more, etc. And then if you plot it on top of a entire
Let me
sequence.
let me interrupt you.
Yeah.
I just want to show this one because it's a bit bigger.
Yes.
Can you see this one?
Right. Yes. Yes.
So
Similar.
this is, yeah, this is on Stevens. This might not be exactly, but I see the
Right.
lambda of 2.
And the
Um,
interpretation here, look, it catches the first peak that if you just
mm-hmm.
focus on 4 years, you have a hard
Yep.
time to explain it. It's able to explain the second peak. Now, the third one is not really, third and fourth is like one big peak. It says, well, what it looks to most people like 1, 2 peaks is actually, or even 3, because there is this little one in the middle. It's a
Mm-hmm.
huge big one. So it's possible, that Terra is because of these subharmonics, right? It tended to have a peak, but then there is the influence of a faster cycle that made it have like a kind of an intermediate oscillation, and then it peak again. But actually, it's one. You see, in fact, you see how the green line, that is a faster oscillation underneath, right? It's related to the slower oscillation by a factor of 2. And when you do that, then you see the 2 peaks. But the 2 peaks really is an illusion, because it is a dominant frequency and these kind of additional frequencies that make look like there are faster oscillations. But it's really the cycle is slowing down with some sub-cycles, let's say, some temporary local cycles that are a little bit faster. And then, and in fact, if you add them together, it is not what Steven has done here. So the difference with what I'm showing, if you want to go back, or ask your question, and then if I'm sure you have
Yeah,
some questions.
we could go in a lot of directions here. Firstly, I think a lot of people would have trouble viewing that 2017 into the 2021 peak as one total one, just because it's counterintuitive. Let's say,
I know.
a lot of people like to debate, was the first or the second peak of 2021 the real peak. And if you look at a lot of different things, like there's a lot of different models that can show different things, but the March 2021 peak seemed like the real peak. But again, here you're lumping both the first and the second peak of 2021 all into this same large peak. So my first question would be, if we presume that this is sort of let's say a valid theory, explain to me again, just in sort of simple terms, where does your eigenvector of 4.12 fit into this?
It's because it's seeing one of these oscillations as a main oscillation. That method, if you look at the oscillatory components, they are really complicated, and there are 6 of them, right? So it's not ideal in terms of studying in a systematic way what that oscillations are, but and this is why we do this log periodic as an alternative way of finding out this oscillation. And this, for example, that spectrum that I show you, it's so clear, right, by naked eye, that there is a huge big peak in the log periodic spectrum. And that log periodic spectrum means it's not going to be a normal oscillation. It's not going to be a fixed oscillation. In time, it's going to expand, right? And it's going to have this subharmonic. So they are there, the main problem we have here is that we have only few oscillations. And every time you have few oscillations, you can do curve, you can do curve fitting, overfitting. So
Yeah.
it's kind of it looks very
Let
nice. It looks good, right? With good oscillations, but there is already some things that we are adding here, like this interpretation that actually you have to lump these two. What most people will say, well, that were 2 cycles, right? We are saying no, they were not 2 cycles. It was just one big event according to this theory that maybe can be subdivided in 2 events, because the subharmonic, you see how the green line, that is the subharmonic, it does point to 2 peaks, and it actually coincides with the 2 peaks. And so if you switch, if I allow me to switch to my slides.
But yeah, let me just one question here, and I do want to derail the whole thing because I want to go back to your call of a price drop in November of 2025, which I think you made, which is pretty good. And I'm not sure if it's related, but firstly, if you're gonna go to the subharmonic as an idea, when do you go to it and when do you not? Because obviously the subharmonic is not fitting the peak of 2013. Right.
So
the green line is very much under.
You have to. This is why I wanted to show you a slide. If you allow me.
Yeah, I'll go back to those. Yeah, hold on.
So it's kind of useful to.
Sorry.
Yeah. Maybe I need to click on my slide. Now, okay, now you see it, right?
Yeah.
And maybe I can make it bigger so it's easier to see.
Yeah, try to maybe go full screen.
Yeah. And is it easier to see now? Maybe.
Yeah, I mean, can you just take it to one page even? Yeah. Even more, I would say. Just zoom it to where it shows like one page, basically. There we go.
Okay. So let's go to this graph. See if I can. Yes, this one. You see here I'm also showing the subharmonics, but I'm actually adding them. That is the real way of doing it, right? It's really not, because these harmonics, they are not acting independently. The real oscillation that you're observing is the total sum of all these components. And now you get this red one, okay? And notice it's almost crazy. I get this peak, the price is not super easy to see because there are also these uncertainty band, but okay, here is one peak, here is the other peak, here's the other peak, here's the other peak. It gets all of them. It gets this one, it gets this one, it gets this one, this one, all of them. Here, maybe this is easier to see, right? Look at this. This one, the smaller peak here, maybe it might miss this. Maybe this was something else, some local event that doesn't have to do with this oscillation. But look, it got this, it got this. In fact, even there is a little bit of a bump there. It got this one, it got this one, it got this one, it got this stuff here, a little bump here, this. It gets everything with adding 3 subharmonic. So if you look, it's like a complicated behavior that there is not that a single wave. There are this wave plus this. In fact, this is one of the reasons why I started to study this long period, because I was seeing this from 2010. I studied a lot of this stuff in my work, where you see a frequency and then you see some side frequency. We call them side frequencies. And so there is this main peak here, and then there are these guys here, right? And they seem to be related. Like it's not by chance this is symmetric, and then you have these other two components here, and it seems that it's something that is happening over and over again. And so the real pattern, the real oscillatory pattern, is not a simple wave. It's this more complicated oscillatory pattern that repeats itself in time. And so when you do that, then now you see the structure, and it's not so crazy to think that this is really one big event with 2 sub peaks, right?
Yeah, I mean, it's elevated over zero, that's for sure. Most of the time.
Yeah.
Most of the time. Listen, let's derail this entirely, because I think it's, I want to come back to it, but in light of, and maybe it's related, maybe it's not, but I've been meaning to ask you for months, because, a lot of people declared the 4-year cycle dead. And again, I thought you were reviving it with your eigenmode 4.12 calculation. Maybe it's more complicated than that, like the 2 to 4. But that's one question. But I was very, very cautious to say that, the cycles are over and it's a new permanently all-time high Bitcoin price. And a lot of people that were saying that had no idea what the power law was anyway in the fall. Some people did, but a lot of people didn't. So I was very cautious about calling at least the 4-year cycle dead. But if I recall, you made a call that there was going to be a drop in November, right? So let's, if it's related to this discussion, I'm keen to continue it. But I sort of want to do it now, because it's I think it's just a very good sort of autopsy to do at this point in April. So do you have anything that you could say about what you were seeing in October? Does it relate to this at all?
It does, because from these graphs, so when okay, the story goes like this. I started with this log periodic understanding early on. Then I changed my mind because I knew that as stock to flow was not the right model. I was never converted by it. I knew that there were problems with it from the beginning. Then eventually I saw more and more problems. But the hash rate story seemed to make sense, in general, mostly psychologically, because and also maybe not much of impact, because that is something that I don't actually, we have a data. It's not a question of believe or not believe. Everything I say, I always try to support it by data, right? There is data to show
Same.
that the change in the supply doesn't have an impact on the price. You can show it in 10 different ways. Maybe very early on, but not now, and for sure not the last few cycles. But there is other.
There is data though to show that it does. If you look at the price, the market cap divided by that data.
I would like to
So
see it sometimes. Share it with
yeah,
me, and I would like to analyze it. What I did,
yeah,
I was able to show, for example, the issuance itself plotted as a function of price, and what you see is very clear. There are these regions where the variation in issuance is so enormous. It is almost similar to what you get when you have an halving event, and the price in this region stays. The price changes, the issuance, it's kind of similar, right? But with big variation, and there is no correlation at all. The price is not affected by the issuance between the halvings, right? And between the halvings, the variation, because the difficulty adjustment takes a little while to adapt, is not affected, doesn't affect the price, and you can show it. And then there are this sudden jump, and if you make a plot of the issuance versus the price, it looks like there is a correlation, but simply because the issuance just jumped, right? So the issuance, let's say stock to flow jumps, and it goes up, and the issuance goes down, right? So it's should be inversely proportional to the price. But it's an illusion. That is my entire criticism of S2F. I've wrote entire medium articles on showing why this doesn't make any sense. But
yep. I agree with you.
yeah. But anyway, so if you have other data showing that the halving has an effect. Now, of course,
It's not the halving. It's just the ratio of the revenue that miners get to the market cap. Also the fees, but it's not a halving driven indicator. That's my point.
Right.
So
Now,
the reason,
this is one of the things I was saying, that there are reasons to think that the halving is an important inner cycle for Bitcoin, also because it affects the revenues of the miners. It's all miners related, right? Has to do with the revenues of the miners, has to do with when they plan, for example, in changing their machines, right? There is every 4 years we need to buy a new machine to keep up with Moore's law, for example, also because there is wear and tear of a machine. So it's kind of like a production cycle, right? That is inherent to Bitcoin. So it does have an influence. And in fact, it's part of why even that log periodic oscillation is related to the 4 years because it's 2 pi times 2, that is 8, right? It is close to 4. It's actually 2 times 4. Anyway, it's like one of the component, one of the recipes, right? But it's actually more complicated. These oscillations tend to be longer and longer. That is some of the evidence. The problem, like I say, which model is correct? Is the log periodic correct? Is the periodic correct? We don't know, because we have too few oscillations. That is the problem. With the power law, you have 5,000 data points or more, right? Almost 6,000 data points. With the oscillation, you have only three or four, and so it's very difficult to distinguish. Are we in a periodic regime? Are we in a log periodic regime?
right.
For sure, the oscillations are there. It's so easy to see from the spectrum, but the right interpretation, it probably it will require one more cycle, to kind of distinguish between the two. And the log periodic oscillations is making some prediction. That is how you should do science. So, for example, it says, but the end of 27, we should have a peak. We are supposed to have a peak of the log periodic oscillation. So the next peak is actually at the end of 2027. So we will have to see. It will be a very important test for this theory that actually we have a log periodic oscillations. So uh, just
So
because of
yeah,
this
I want
influence
to.
of a hash rate of a halving, right? I abandoned my log periodic understanding. I went to the periodic, and if you, I don't know if you follow some of my work, and at a certain point, I even made a prediction about the price. There was some misunderstanding about that. My main point was, if you look at the residual, right? These are residual that you're actually showing here on the graph, on the top left, right, of our
Yep.
screen. You can see that these peaks are decaying, right? So forget about the log periodic oscillation, etc. So my interest was, is there a pattern that describes this decay of the peaks, right? And there is actually, you can see, because this kind of a log, there is the log of a or percentage here, right? Is basically the same thing. They are related uh, of the of these peaks, right? They look kind of like a straight line. So that means there is an exponential. And in fact, actually, you can fit an exponential through these peaks, and you can project that exponential to the
Yep.
future. And
The
if you
decay.
if you did that, we should have had, because you can see, right, where actually we ended up instead where we should have been. You can see, even with your naked eye, we should have been much higher than where we ended up if you extend it. Like, imagine there
Yep.
is an imaginary line through the peak, you extend it.
Should be here somewhere,
Yeah. And my calculation
and we
was
weren't.
it should have been 80% from the power law. So my argument, when many people misunderstood because they thought that it was, oh, we should go at least there. No, my statement was, given this decay, I think we don't go higher than that, right? Now I have to be honest. So in 80%, the power law was would have been around 120,000. If you do 80% of that, you get 200,000. And so I say, by the end of the year, at most we go to 200,000. And this was a time when, this was at the beginning of a bull cycle, when basically we had the ETF, etc. Everybody was going crazy and saying, oh, 400,000, 500,000. There was the 444K prediction. Some people were saying even a million. And they say, it doesn't look like, at most we go 200. And in fact, what happened, that we stay glued to the power law. For almost for several months, we follow the power law almost to
Yep.
a dot. We were like moving along the power law. And in fact, guess what, right? The value that we got around October, when we had the peak of this cycle, was 125. It was exactly what I knew that we were going to be during this time, because this is what the power law said. So the power law actually predicted where we were going to be in October, November, right, Q4 of last year. The problem is that most people thought that we were going to have that plus something, because we were
Yeah.
supposed to deviate from the power law quite a bit. And to be honest, I was surprised myself. I
No,
thought
I
that
was too. I was
I
too.
thought we were going to at least 150, 160, maybe even bet 200K.
I had 250 as a possible, but it was. I
Yeah,
totally agree with you. Let me stop you though, because our friend Plan B predicted a million,
I know.
and I just got to show it in case people don't think that those things
He
are
was making fun of us, right? He was making fun of the
real.
power law people that we were.
Yep. Uh, God, why is this? Hold on, let me stop that. Redo this one. Here we go. This is just for fun. Just for
Yeah,
fun,
sure,
looking back
sure,
at this.
exactly.
So this is a Coinbase, no, it's a Binance article that they saved. I looked back, I couldn't find his tweets for this. It's a good thing other people saved it. Of course, it would be on the Wayback Machine, but it's September 2024. So Trump is about to come in. Everybody's about to get their hard on for Trump doing all this stuff, which he never did. But here he says, in April, this means April 2024.
Right.
No, sorry. It's September, but in April 2025, so the 4 year, right? He predicts Trump will start building a strategic Bitcoin reserve, pushing the price to an astonishing 400,000. Finally, between July and December 2025, a wave of a face-melting FOMO would drive Bitcoin to the $1 million mark. So there it is right there in black and white.
Yeah.
The perennial, just terrible predictor keeps doing it, and he did it based on his erroneous stock to flow model. So anyway, I had to do that there.
Yeah,
but yeah, I do want to get back because I was the same, and I said it many times. Like I was having fun, like in the summer of last year. Like, oh, okay, we got all these percentiles. We're going to be up here. How many days have we been above this percentile? It's going to happen. This and that. And I was preparing on my stream for that as well, just not to get too much FOMO, too crazy, but let's just prepare for the extremes.
Yep.
Like you said, it didn't happen. But what I'm really curious about, and I'm not sure if it has to do with the harmonic model again or the log periodicity, but you did call for a drop in November, right?
Yep. And
so do you have a chart on that?
By the time I started to see that, we were not going there, that we were not leaving that power law, I went back myself and I started to look at some of these log periodic oscillation and also what Stephen was doing and so on. And the main thing that we were getting from this oscillation that we were not supposed to have a peak. In fact, even if you take some of these subharmonic, they say, okay, if they get the bottom at 16,000, the models, they have this bottom at 16,000, then you go up, and basically you're touching the power law. This is what these log periodic models were saying. And in fact, then they drop. In fact, I can show you a trading view projection of that.
Yeah, I just want to see it because I'm curious on what your Schelling point there was, because it's to my mind that's a fantastic call.
I think you have to stop sharing what you're sharing because I'm trying to share and
it should be stopped. Everything should be stopped.
I don't know. I'm not.
Hold on. I put a different screen share up for you. Maybe you stop that one.
Okay. How do I do that?
Click the same screen share button.
Doesn't know. Oh yeah, I think I know. Stop. Okay, yes. And then I will share my. So I made this trading view indicator. You have your own beautiful indicators, custom made, right? I'm using trading view.
Nothing wrong with that.
And so this is actually the log periodic in trading view. And in fact, let me zoom out to show you. You see, this is what I was telling you before, how crazy this model is. It's a little bit cheating because I'm adding a little bit too many harmonics. And the clean way of doing this will be to look at the main harmonic and say, then I'm adding the number 2, the number 3,
yeah,
and not exactly this a little bit shifted harmonic, other peaks that probably they have some other information, and the information could be external one, and something that I want to study myself. I want to understand why they are shifty relatively to a pure second harmonic, third harmonic. Is that some kind of interaction? That is another way, very physics like to think, oh, there are some external influences, there is some internal oscillation that is typical of a system, but then there are external oscillation that create some kind of interference, right? So that needs to be studied. So I'm adding the observed frequency, and then you're getting almost a perfect predictive model. Like, look at this, right? It's getting this one, it's getting this one, this oscillation here, this one. And again, the interpretation, you see, it's the same oscillation. See how fast it was here, then it's getting stretchier. It's almost like basically two main peaks, right? And this third one. So this peak is this one, this peak is this one, and then This other one is this one. You see how are getting stretched, and now this
Yeah.
one is getting even
Yeah.
more stretched. Right now, all this is big. This big oscillation, like we say, this is like one big event according to this
Yeah.
interpretation. Now,
Right.
this is not predicted because you know what is this, right? That is COVID. So nobody
Mm-hmm.
could. This model could not predict COVID. What is cool is that the floor, right? You're familiar with. I don't know if you use it in your models, but we say there is this floor that is about
Are you using the
50%, one sigma away, and they did even during COVID, they didn't go through that. You're using it. You're using it
what's
yourself.
your floor? What's your floor defined as?
I think actually the best way is to just calculate one sigma
One
from
sigma.
yeah.
Okay.
It's much higher above, right? You can go all the way to 3 sigmas, but it's very consistent below 1 sigma.
Yeah.
Yeah.
Okay.
But you see
And
now,
then
look at this, right? These
yeah.
models say we should not have gone higher than the power law. This green band is, by way, the confidence levels of this model. But you see, the model, it kind of predicted where the top was.
Yeah, that's incredible.
And
So
then
how
it tells
many
us that we are going
harmonics?
down. In fact, actually, it's telling us that
Yeah,
we are
which
supposed
I
to have a bottom in August.
which I can absolutely see happening. How many harmonics do you have rolled up into this?
3.
3.
Yeah.
And
Okay, it is not a lot. It's not a lot.
your you can do predictions on the harmonics too?
Well, you can extend this model all the way to 10 years from now. Like I
But
say, if you
the
extend it, unfortunately, TradingView doesn't allow you to do many months or many years, but you can do
no,
it offline.
I just mean the math of your t of your x values. Like you can extend a normal regression out
Yeah,
with the imaginary lines and everything. You just keep extending it.
right. You can. And in fact, if you do it offline, one of the main prediction is that we should have a peak, right? So we're going to have a bottom here, and
Yeah.
then that will be the end of this, the bottom of this cycle, basically, and then like the equivalent of this bottom here, right? Or this bottom here. In fact, you see, the bottom here was at 17,000, close to it, right? It's within the 17,000 was within the confidence level, and then it will continue to go up and reach a peak at the end of 2027. This is when we are supposed to have the next peak.
Yeah, it looks good. It looks good. All right, now that we've looked at that, which is super helpful, and I congratulate you on that call because I was happy with myself that I wasn't in a euphoric mode like in the summer and the fall because a lot of people were, but or saying that the cycles are over. But then again, just because I like to hear things more than once when I'm learning, your 4.12 on the eigen mode,
Yep.
can we, in simplified terms, layer that into this, or is the
Yeah.
4.12
Because
not going to work?
even the harmonics, right? We have harmonics. They are all multiple of this four. Four is the magic number because right, basically what he's saying, right? He's saying, well, half of 4 is 2. Is why you got this distance is 2 years. Then that 2, according to the stretching, became 4. Then that 4 became 8. But wait a second, you have also the second harmonic, right? The second harmonic means actually faster. That means 2, right? So what is supposed to be 8 now is actually 4. So when actually the log periodic frequency should or period should be 8, if you're observing a subharmonic of that basically are these two peaks, right? These sub peaks. Now that looks 4, and so
If
that
we
is
looked at
what
that in log.
right, and but at the same time, our eye and the eigenvectors were seeing that say, hey, I see a big strong signal at 4 years, right? And it's picking up that. It's just that it doesn't have a language of a log periodic because what if you actually look at how these other eigenmode looks like, they kind of look like this. They look very complicated oscillation. And so you will look at the complicated oscillation and not make sense of it, because you say, what does it mean, right? Does it have even some periodicity? Because if you don't know this idea that you are looking at something that is being stretched over and over, you're not seeing any periodicity here, right, in these things. But then you say, oh, it is log periodic, it's not periodic. So the eigenmode method doesn't know that. And so this is why you always want to do more than one type of analysis, right? When people say, oh, this method is the best, like, oh, quantile regression is the ultimate. No, uh, all these methods are valid because they show different aspects of the same thing. It's like, I make these
Right.
analogies like saying you're going to the doctor and the doctor is ordering x-rays, blood samples, urine samples. These are all different ways of understanding Bitcoin. The story is very similar. There is this very long term that is undeniable, and is the power law. And then there are oscillations. The problem that we have right now, I think, is the interpretation. Is which camp is right? Is the periodic camp right? So the 4 years, right? Some people say that is intact. The interpretation of that will be, yeah, we had a 4 year cycle. This was last time, and now this is 4 years later, we have this. I'm not convinced, because it looks like, a wimpy cycle, right? It doesn't
Mm-hmm.
look like a very strong cycle, because you're seeing a subharmonic. You're
The
not seeing
sub,
the
yeah.
main harmonic. And so it looks like four, but it's not really four. It's like one component of four, you know. So yeah,
And the 27 year end would be a main
it
harmonic,
will be, yeah,
considering,
these were the main harmonic peaks. Yeah. But it's
because
the
that
one
is
that
a,
has the biggest amplitude, right?
but that is conceptually, at least in linear space, hard to think of, because on the odd year
I know.
after the dump, it's never been an explosion except for 2011.
Yeah, and that will be a very good test of this theory.
2011 would be the only time.
Yeah. So if that we were 2011, so 2011, are you thinking? Sorry, let me
Because
see.
2013, 2017, 2021, those are on a 4. I'm just going on
Right,
basic
right. So
4.
you're
I'm not talking
thinking
about
this
log.
peak, right? This peak.
Right.
Yeah.
But that would be the only time that I can
Right.
think of that would
And
line up
and
with
this is
your
why
2027.
already there is some advantage of this theory, because a four periodic theory is not able to include this one, right? There is this
Yeah.
work by Leo. I don't remember his last name, but
Yeah, I've just heard of him actually.
yeah,
Hart, I believe. Leo Hart.
Leo Hart, and what he does, that I was criticizing him. He takes one of a frequency and almost by hand, so there is not really uh, like a theoretical basis for it, but and sometimes it's good because people have done that in the past, and then you go backwards, say, oh, there is a reason why we should do that, right? There's a physical
Sure.
reason to do that. But he did a mathematical trick where he extends the frequency and is able to catch this one and then the other ones, etc. So he doesn't use the language of log periodicity, but in a kind of indirect way, it does. But you see, the language of log periodicity does it naturally, completely naturally. You don't have to do anything artificially. You're just saying, yeah, there are these log periodicity that seem to be inherent to Bitcoin. They are part of a spectrum, and then the the difficulty here is to convince people that this was one big event. That it was not. You will not have even seen. You probably have seen like one big peak if you didn't have also these sub frequencies, right? This sub frequency creates these sub peaks. So these were peaks, but actually were sub peak,
Mm-hmm.
not real peaks.
I just want to say it's lovely to hear the birds in the morning on the West Coast.
I know it is could
Haven't
make a lot of noise. Yeah.
haven't been there in a while. Listen, I want to show you one more.
I want to say one
just
thing. If this
yeah, yeah,
theory is, and but we can conclude here this talk about the log periodic stuff. But if it is true, it will be super cool because like I said before, one single equation will explain both the long term and the oscillation.
and it would be again, like I said, 2027. That should be the only model that would match
Yeah,
the 2011 peak as well.
correct.
Since 2013, 17, and 2021 are all.
Yeah, and then also the other interesting part of
this
it will
4 year.
be these are not things that are influenced from the outside. Maybe they interact with things from the outside. Maybe the phase, like why it happened here instead of happening somewhere else, the phase or the particular place where the peaks are happening. But the periodicity itself, it's internal to Bitcoin.
Yeah.
It is like some property of a system, So it's a very cool idea. I hope it's true. But hey, we are here to study Bitcoin, not the other way around. I will know.
Yeah, absolutely. Yeah. That's fascinating. One more. I just want to show you back on the.
Yeah.
It's only. I only want to show you one chart, only because I'm thinking of it, and it's not fresh, unfortunately. But this is where I would say I could tell that the 2021 peak in March, at least, was the real one. So the black line, this line is what I call the PSR.
Yep.
I actually started this even before any of my other models. And so it's very simply, it's a 12-month rolling sum of miner revenue and fees. And the vast majority, 99%, 90% of the time is miner revenue from new coins. The rest is fees, but that's not that often. But anyway, you put that in USD.
Yep.
Right? Rolled sum over trailing 12 months. And then how many times does that go into the market cap at any given time? So it'd be interesting. Maybe you would think about doing this with your harmonic model as well. I've just done a simple percentile, which is not even, it doesn't even work on log scale because it's, or log because it's more on an exponential type of a thing. But in any event, you have the 2011, you can only start, my data starts in May 2010. So you get basically May, you get this 2011, then you get the peak in 2013, two of them. And notice how they're like much higher together, by the way. Than, not like the price where that's different. So that both peaks are kind of the same.
Yep.
And then 2017's peak, 2019's looks where it does. Then 2021, you see it's a much different than the price. Okay. And then here, unfortunately, I have this cut off from like February, so I can't show you anymore because I'm redoing everything. But this is an argument that there's still something going on from a miner revenue perspective that I do think is important. And,
absolutely.
I'm just thinking from a shelling point, like from an idea of a shelling point, or, any industry would be severely affected if their revenue was cut 50% overnight. Yeah. So, though I know the arguments, and you know them as well, that, it's not really that much. The miners' coins don't do that much. To me, I just wasn't buying that all in total because there's so much sort of riding on the 4 year, and you can still make models of what they get relative to the price, i.e. this black line. And it might not, be perfect. I would be really curious, if you just took that data, the black line, and run your harmonics on that, how that would look.
Tell me one more
there are many ways.
How you calculate it?
It's you take in Bitcoin every day the new coins.
Yes.
Right, and then you take the fees that miners get.
Right.
So you would get a daily total in Bitcoin multiply that by the dollar price of the day. That's the minor revenue of a day. You repeat that for each day in a 365-day window, and then you roll it. You will get that figure. And so and then that figure, which is the minor revenue, it will be something like $18 billion at the moment. It's 18 billion.
Mm-hmm.
So how many times does 18 billion go into the market cap? And so it's equivalent to, in the financial world, it's a PSR, price to sales ratio. You can either do it on a per share basis or a total basis, but I'm doing it on a total basis because it's easier to conceptually think about. So whatever the market cap is at any time, divide that number by this total sales or total revenue of the network in dollar terms. And so you'll get a line that looks like this. But you could also run the harmonics on the revenue figure itself, which I'll pull up. I don't know if even that's working for my... The figure is about 18 billion, 17 billion at the moment in dollars. So that's the number, yeah. But as far as the nice multiple, this is what it looks like until February. It's down below, somewhere here.
And you're showing me this in a linear chart, right? You're doing it.
No, this is log linear.
Okay, log linear. Okay.
If I did linear, it would look a lot more like that.
Mm-hmm. Okay.
And so there's the price. You can see how the price lines up with it. You'll get differences.
Right.
Not necessarily. You just have to see how they might play with your model when that. But
so why you were saying exponential, because it curves, right, in a log chart, in a log linear chart. So probably is a power law.
It's a 72% R squared.
Right.
It's not great.
Yeah.
It's not great, but yeah. So, but anyway, that's at least what I was always thinking about in the back of my mind when people talked about the 4-year being dead. And then when you came out with your eigenvector, I was very intrigued, because that obviously points to something very different about what the 4-year actually could mean to the price. So I don't know if you have anything you want to say based on what I've just said there, but that's what I was thinking.
I mean, I'm sure that 4 years is one of the internal cycles of Bitcoin. Now, how that plays with this idea of log normal is just, like I say, it's, the 4 years is going to be fixed because, of course, right, every 4 years something happens. But then there is a tendency, maybe it's possible that one way of thinking is that the system doesn't react so hard to the 4 years itself, right? It's still being there, and the way for the system to kind of digest the impact of the 4 years is distributing it over longer and longer period of time. So it's basically stretching it out. Because actually, like I say, the main harmonic is 2 years. That is related to 4, right? So it's
what do you think about that? What do you think about this comment? It's external now. Let's jump to an external. Yeah. The refinancing cycle in credit has occurred roughly every 45 years. Mm-hmm. 2011 was an outlier year where the GFC disrupted the 4-year flow model.
So the other thing to think is, first of all, why 4, right? It's possible that Satoshi has chosen 4 because there are market cycles, right? Economical cycles. 4 is something that actually many other things are happening, right? The elections, the World Cup, etc. 4 years is a cycle that humans don't consider it too long or too short, right? It's something pretty natural that happens often in human culture, right? Now, the question is how that 4 years that is internal to Bitcoin and it's not synchronized to particular event outside interacts with other things that are also 4 years, right? So that is something that I don't think anybody explored, because, for example, the day that there is the halving itself, not much happens, right? There is not a sudden shift of anything. It's usually, for example, the different peaks that we observe, right? They are 4 years, but they don't happen at the halving. They happen many months later, right? So that means that probably there is some kind of influence from external cycles that shift where the peak happens, right? So the periodicity is there, but the phase, that is the exact place where the peak is influenced by external event. So this is an entire topic that should be studied. We have tools like we can say, okay, this particular cycle has this much of an influence, right? You can take all the major, like PMI, for example, right? You can say, okay, there is this particular macroeconomic cycles, and I know how it's behaving, how strongly coupled, that is the language of physicists will use, with the Fourier Bitcoin cycles. Are they in phase? Are they, and I already started to do some studies like that, right? The main problem is the same. While we have thousands of data points for the power law itself, we have only 3 or 4 cycles. So it's very difficult to do stats when you have just few oscillations. It's very difficult to interpret what is going on.
Well, it's very interesting, and I'm keenly curious to see how 2027 could play out. And I totally think that you're right on about a summer bottom. And
it's interesting because it's not where everybody thinks that should be at top.
It's a clear discrepancy, regression.
So if it happens, then it's a very strong evidence for this model.
Yeah, very interesting. Okay, back to the power law.
Yeah,
I was talking to Plan C about some different things. I think he might be coming out with some more work. I don't know if you've seen. He's experimenting with different ways.
Can I say something in general about that approach? I think he's missing the point, right? Because first of all, I don't know. Tell me what you think he's doing. So maybe you have a different understanding. Where is he going?
Well, I'll summarize what I talked to him about, because I've seen some of his stuff and I asked him. I want to have him on as well to talk about, but I see a few different things that we can talk about that we get away from the core of what I guess you and I were looking at, 8 years ago. But basically, you have the OLS, then you have the quantile, say the 50th, all right, where you have a median. Then you could do something which is like this Jacobian weighted, which is what he's talking about doing, where you basically put more emphasis on the early because it's log-log, and so there's, later series get upweighted under the current power law, which again, you can argue if it's valid or not. So this would put more upweighting on earlier series. The problem with that, of course, is it's thinner data with Bitcoin. But if you actually do that approach, this is now the third adjustment I'm talking about, you would actually take the OLS higher. You would take the weighting higher because, as you and I know, the slope was way high in 2011, 12. It was, 10 or 11, 12. That's the third one. Then you have changing the starting date. All right, you saw Sminston did this last year. I've done it as well. I mean, better people have done it, but straight up July, I think, would be the highest R squared, July 2009. Or as a subset of this fourth thing, you could just go into block time. I think Stephen Perrineau has done that as well.
Yeah.
So that's block time. And then you translate it back into, calendar time. That's 4 things. And then the 5th thing is the decay. So I count 5 things. If we just count...
and it's all irrelevant for many reasons. First of all, like I said, what I said before, right? Like he has a big deal. He makes a big deal about OLS not being the ideal method, etc. Nobody ever say that is the ideal method. It's a discovery method. We use it because it's the simplest possible way of calculating a regression. It's when we discover the power law, at least when I did it, I used the OLS simply because I wanted to get a feeling of what was that exponent, right? This is how we discover the power law. Then you say, look, how the data looks like. Oh, there are the residuals don't look normal. Okay, because there are these big oscillations. Are there other methods that reduce the importance of this oscillation? Yes, there are many. There are Bayesian regression. There are quantile regression. The quantile regression that it does is not a different way of finding the power law. It's just one of the many ways, because the input that it is using is log of time and log of price. So when it does the quantile, you're finding the power law because the input is log of time and log of price.
Yeah,
All these quantiles are power laws, all of them.
they are.
Uh,
They are.
and now because of the way the quantile works, the main line in the middle is going to be the median. Is the median a better way of measuring the power law than a mean? No, it's just another way. It gives you a slightly different information. It's like I'm taking X-rays, I'm taking blood samples, I'm getting different understanding of what the power law is and what it represents. In fact, this obsession of focusing on that middle line, it's actually missing the point. One of the things I did that is so much deeper than all this stuff, because it goes to the art of what the power law is about, is to understand the dynamics. So what did I do, for example? I calculated what is called the local slope. What you do, you take the returns, so you take price today over price yesterday, right? This will be the return. And then if you write it, you can follow me mentally, right? So if the price is supposed to be a power law, so P2 equal A T2 to the n, right? And then
Hmm.
P1 will be A T1 to the n. You take the ratio, A goes away. It is really cool because now you have only one parameter, and now you have T2 over T1, right, to the n. So that
Yeah.
quantity T2 over T1 to the n is a deterministic quantity. Is this kind of big deal that we are saying that Bitcoin has this deterministic component. So you take it and you divide it by, you take the log of both sides, log P2, so the log of the returns, and you're left with log P2 over P1 equal n times the log of T2 over T1, right? You divide your returns by the log of T2 over T1, you're left with n. N is the exponent. Now you can think about, because if P2 and P1 were perfectly following the power law, so the power law was a perfect straight line that is impossible with something like Bitcoin that is stochastic, right? It's random. Yes, it's oscillating around the power law, but it's still oscillating. So these P2 and P1 are going to be random numbers, right? And they are going to generate a random n. So in general, n is a random quantity. Now you do the distribution of this n, guess what? The average value is 5.8, right? And now you have a complete characterization of Bitcoin behavior, because now you can measure the distribution. You can measure how spread the distribution. It turns out it is a distribution with very big heavy tails that explains why sometimes you have days with 5, 6, 7, 8% changes in both directions, right? And now what do? You can use this and do a Monte Carlo simulation of entire history of Bitcoin using this distribution, because you can throw the dice, right? Once you know how Bitcoin behaves, you can throw the dice over and over and over again. You have this deterministic component, and you can reconstruct millions of alternative history of Bitcoin. Some history, some extreme history that are very rare, go all the way to a billion Bitcoin right now. Some history
Yeah.
go where a Bitcoin is $0.1. Guess what?
Yeah.
The median of all this history is the power law. So you
Yeah.
reconstruct the power law without any regression. What somebody like Plan C will say, it, it's an intrinsic property that has nothing to do with the regression, right? And we don't even need to use a particular day where to start this process, right? It's just an intrinsic property because it's about the dynamic, the change in the price is the dynamic, and the power law shows up there. So it doesn't matter where we are relatively to the power law. The important thing that the particular growth of a process is according to the power law. And I did another graph. I show visually these little slopes, right? They look like little vectors. So it's almost like wind. I don't know if you saw this simulation. It's so incredible. You see all these vectors that are going up and then down and then up and then down. But if you take the average of all of them, they point in the direction of a power law. They are parallel to the power law. So my point with all these is that line that people think is the power law is not the power law at all. It's just one of the many ways the power law shows up because it represents some kind of average pattern, average path, etc. But saying, making a big deal that it should go a little bit lower, a little bit higher, is completely laughable. It's not really a big deal. The big deal is that the dynamics of a power law is consistent. And guess what? For example, if you plot this n, this value of it that shows the dynamic over time, it's incredibly stable. It's the most stable parameter that we have about Bitcoin. Has been stable. In fact, you know, if you take the first 2 years, 3 years of data, and you're trying to fit a regression, right? Like you will not be able to see the power law at all, or if you force it to go to be a power law, the value of n will be crazy because it's dominated, for example, by that bubble in 2011, right? The data is dominated by that. Well, this method doesn't care. From basically since we had the data, you immediately see the stability of this parameter, of this n, if you do it in this way. And it's really cool because it shows how stable it is in time. You can do so many different tests. It's part of a paper that we publish, by the way. And then you can also plot the variance of this parameter, right? And you know what is very interesting because early days, up to 2017, the variance was smaller, but is counterintuitive. Like the reason why the volatility of Bitcoin actually seems smaller now is because what is happening is that the returns are becoming smaller, and so the change relative to the if you take the absolute values of a volatility, it seems smaller because the returns are smaller. But if you do it relative to the returns, actually the volatility is bigger now than in the early days, and it has been stable.
Wait, what do you mean about that point? Because the volatility,
the relative
relative.
volatility. So if you take the volatility relative to the returns, so for example, this n in a sense, it's a normalized return, right? You normalize the return by the decay due to the power law, right? You know that if you plot the CAGR as as given by the power law, because you can say, hey, what is the annual return predictive by power law? It looks like a curve.
We'll get there. I have that question for you too.
And you have probably you have that curve too, right? Among your
I have plenty of those curves,
right? So and it fits the historical returns, annual returns of Bitcoin, right? Very well. Now, if you adjust for that, that is basically what I'm proposing, right? I'm saying take the return, adjust it, normalize it by the decay due to the power law. Then you have this quantity that is a normalized return. It turns out, by the way, that is the slope, that is that n. It's the same thing. It's a form of normalized returns. That quantity is stable in time. But then if you measure the volatility of this quantity, as it was smaller the first few years, then it jumped in 2017. Something happened in 2017. Very clear. It's really cool to see. There was some.
Do you have a chart of this that I can look at it?
Yeah, I can show you. I can go back to my.
Just want to see this.
Yeah, I can show it to you.
Specifically on the return volatility.
Actually, from my book. I'm showing you pages from my book.
Fantastic. Everybody will be checking that out, I'm sure.
It's called The Physics of Bitcoin. So I'm going to.
It's not out yet, right? Or it is out?
People can pre-order it, and it's going to be out on the 10th. Yes.
Fantastic.
Okay. So this is the graph that I wanted to show you. I'm going to show
3 days away.
It's really cool, and I think this is really the core of the core of the core of the issue. This is the Bitcoin should be understood with this language of the slopes. Do you see my graph or no? Let me stop it and share it.
Yeah, no. Do it again. Yeah, do it one more time.
Okay.
Okay,
Yeah.
it's coming.
So it's here. Let me do the same thing I was doing before. I'm going to
Yeah,
make
take it
bigger.
max zoom.
Okay, here it is. So what you're seeing here, right? So let me go full page. So these dots that you're seeing here is this quantity, right? Remember what I'm doing. I'm taking the log of returns, and then I'm dividing by the log of the change in time, right? So in this case, the time that the age of Bitcoin today over the age of Bitcoin yesterday, and taking the log of that. And so I'm normalizing the return by this quantity, right? It turns out that it is n. The value of that is n. It's what they call the local slope. But in a sense, it's a normalized return. It's basically what you are supposed to do every day in terms of gains by corrected by the decay due to the power law. These dots are these values, and they are all over the place, right? They go crazy. And notice what happens if I do a moving average of these values. I get this yellow curve. And that dotted line is 5.86. That is what you get by regression. So you see, this is a method that has nothing to do with regression, and it finds the power law. It finds that exponent. And notice how stable it is from the early days, all the way to today. See, it's not changed. This is destroys any plan C argument that the power law is changing, is decay. No, it's not. You're looking at the wrong thing. You're looking at noise. It's looking at noise. It's not looking at the signal. This is the signal. This is the signal. And you can do it on scales of days. So I'm doing it. See, this is every single day. You can do it on the scales of months. So these are the changes of months, and these are changes over year, 1 year. So these are the changes over 1 year of this quantity, right? And you can see how stable it is. It's incredibly stable. And you see here the variance, like you can see with your eyes. You see how there is a jump in 17? See here is, basically it's confined between here and here, right? Most of the data are within here and here. And then all of a sudden, in 2017, the data go all the way here and here. And again, this quantity is stable. So basically, this is a complete picture of behavior, stochastic behavior of Bitcoin once you eliminate the trend. So you're eliminating the trend, and then you're saying how stable this quantity is, and it's super stable in average, but also in variance because it didn't change since the last year. So in other words, Bitcoin has done exactly the same thing through all the different changes, ETF, the different crises, the Luna crisis, everything has done exactly the same thing since the last 8 years. It didn't change at all. And before that, actually, this variance was smaller, but it's counterintuitive. It's possible that this 2017 is the the institution coming in that brought maybe more liquidity or whatever, and so now there is more change. This is absolute change because yes, the relative change is going down simply because the returns are going down. As you see, this is when you go really deep in the data and you find stuff that many people don't know, or it's even counterintuitive. It's the opposite of what most people think.
Yeah, it's interesting. Let me throw one more thing at you and then come back to the idea of the different ways to look at the power law. Because this actually is counterintuitive to me as well, because power laws, by their nature, they're going to converge. They're going to get like closer to the trend in the future. Whereas exponential curves, they can have the same amplitude, the same residual. Let's say, for example, a financial stock. You can look at Procter and Gamble, 80 years ago. If you draw that regression line through the prices, you could have 20% above the regression, 20% below the regression exponentially 80 years ago on, let's say linear or normal space. as you would have today. So exponential regressions have this consistent volatility that actually holds. And as you were saying earlier about the fractals, this could come back to the fractals as well. They can speed up, and this gets into the super exponential growth, I think, as well, of what Jeffrey West talks about.
Right.
They can go faster and faster till you get to a break point.
Yes.
But that's actually counterintuitive how you say the returns are actually always the same, because just to say, like, for the audience, just like someone who's questioning this, because I'm questioning it, is in normal linear space, power law returns decrease.
Yeah.
Right. I mean, like
they go down
both the residuals,
roughly 1/4 the age of a system.
Right. Right. So just to say that point, that is interesting, the data that you're providing with the normalized n, let's say.
Yeah.
Because yeah, I haven't thought about it that way.
Yeah, it's really cool. It's really cool. And I really think that that n, it's the core of a power law. It's really the best way to understand the power law, because it has nothing to do with where we are on that line. That line can be reconstructed from that data. You see, this is what I was telling you before. What did they do here, right? Once you have this distribution of this n, then you can say, you're familiar with what is called Monte Carlo simulation, right? You're saying to the computer, extract numbers that are taken randomly from this distribution, right? And then what happened? That gives you n. Now you can go back, if you know which day it is, you multiply, right? You do the opposite of what you did before. To get that n, you divide by that change in time. If you multiply, it gives you back the return, right? The log return. So for every day of this history that you are creating, you can reconstruct the gain, right? So if you have, okay, today I did, I was up 10%. Yesterday went up 10%, right? You multiply these gains, right? You do the cumulative compounding of these gains, and you get these alternative histories, right? You get these are all the history of Bitcoin that you can get, alternative universes. I did it, I don't know, this simulation 1,000 times, 10,000 times, how much it is. The color coding is how rare they are. The majority of the paths are in this green, like a big quantity, like 65%. This is like 1 sigma deviations. And then, as you go farther away, they are rarer and rarer, right? These are very rare paths. Now, guess what? If you take the median of all these paths, you get this yellow line, which is the power law. It's really cool, because I'm not drawing the power law here. I'm calculating the median of all these different. You don't see the paths because it's just color coded, but they will be
so many,
crazy lines like this. And now you take the median of all these paths and you get the power law. And there is something profound there, because it says the power law is kind of is a path of least resistance, is a path of least actions. There's a lot of interesting, beautiful ideas beyond that. But it's not really what is fundamental here, even if it is a useful line. What is fundamental is the dynamics, right? Is that when you take all these possible paths, the path that is most likely is the one that is represented by the power law. And it turns out that the real Bitcoin goes through it as it oscillates. It's not one of these crazy paths. And now, even had a conversation that I posted on my Medium with ChatGPT and say, ChatGPT, why among all these possible universes, I know they are rare, but we could find ourselves maybe in this orange, right? Or maybe in this other orange. How come we are, first of all, in the green? Yes, it's more likely, but it's not satisfying. They say, well, because you're calculating all the theoretical possible path, there are other constraints, right? The markets behave almost like a rubber band. If you go too far away and you're trying to go to some of these crazy theoretical paths, there are market forces that you bring it back. So it's obvious, it's and actually this is one thing that could be really cool to study, that you will have oscillations around this line. you know. So in other words, I'm trying to say, guys, don't fixate on this yellow line, because it doesn't matter where we are. If we are going there, right? If we can do up and down, we can go. If the most important thing is the direction, it's how we go there.
Sure. Well, let me put it to you this way, though, because you yourself earlier said it's good to not limit yourself to one model. But those five that I mentioned, right? So you have the OLS, you have the median,
Yeah.
you have the WLS or some Jacobian weighting, you have changing the date or using block time, and you have the exponential decay, which you also brought up in this
Mhm.
interview. Those are still five different ways to deal with
Well,
the structure.
and this is another graph that shows that. I don't know if you see this one. Let's watch this one. Here, this one, I made the point of plotting. I have here Bayesian, Uber, the Tells Sand model, quantile. Look at this. We all agree. We all agree. We all agree. The differences are so small. It again is kind of silly to say, oh, the quantile is the best model. Oh, the Bayesian is the best model. It's like you're co-tailing,
But yeah,
you're,
that's not my question. My
yeah.
question is just how do you look at it? How do you look at it? Do you
That is exactly this.
isn't
Is
doesn't
useful
but
to,
doesn't Steven go on block time, or at least he wanted to go on
yeah,
block time at
because
some point?
and a useful thing to do. And guess what? You get basically the same result. You know, yes, if you look at an individual and you're taking the X-rays, you're taking the blood sample, you're taking the pulse, they are not going to give you completely different results. Are they useful way of looking at the individual? Yes, because maybe they converge to the same idea, but they give you things that maybe one, you cannot learn what you learn from a blood sample, what you learn from an X-ray, right? But they should not give you completely different results. They should talk about the same individual, right? If you have a blood clot, it will come up with one method and it will come up with another method, right? So the
Yeah.
bottom line I'm trying to say, it is useful and they are good contributions to look at slightly possible different results, but both because of my training as a physicist, but also because physicists go to the essence of things, right? The essence of things, will you say that these things are more similar or more different? They are more similar. If the power law was not real, we will see big divergences between these methods. The divergence is not there. In particular, if you look at where the real power law is, it is this lower part. This lower part, the quantile, the regression, everything in the lower quantiles, that is also, by way, associated probably with the cost of production of Bitcoin. So again, we are going back to some fundamental truths like miners have a fundamental importance in Bitcoin. We all agree. We all agree. And the difference, how, okay, we are using this weighting, it's like, it doesn't matter. Okay, sure. Okay, you improve the uh, the correlation from 0.7 to 0.98. Big deal. Who cares? No, nobody. I mean, yeah, okay, you did something that is somehow useful, but it's not a big deal. It's not where the main message is. And if you're telling me, oh, that allows me to tell me that in 5 years from now, Bitcoin will be 235 versus 210 or even at 180, call me when you have a difference of factor of 10, because in the end, the power law, it's a scaling phenomena. So what we care is changes of 10. Basically, we are saying in 8 years, Bitcoin will be $1 million. Do you agree or not?
Yep.
If anything within a factor of 2, it's the same prediction. The errors, in other words,
Right.
another way of looking at this, the changes that Plan C is proposing, and I'm not trying to do polemical with Plan C, it's more pedagogical. I calculated that the changes that he's proposing in the model are smaller than the error itself. When you talk with him, ask him, what are the error that are you in other words, if I plotted here my confidence bands, am I still within that confidence bands? Yes. And if you are within, your proposed change is irrelevant because we are within, unless you have a method of reducing noise. And nobody has that because the noise is the noise, you know?
Okay.
You understand what I'm saying? You understand what I'm saying?
Yeah. So I think the conclusion from your side is that the for your main model and for all the harmonics and everything, you are still using basically the OLS at January 3rd calendar time. That's kind of the main thing that you're continuing with. And you
No,
think
I'm not
it's
saying that at
anyway.
all. In fact, I just say that the main language that should be used doesn't even use regression at all. It's the slopes. The local slopes is the best
Yeah,
way to describe
you
the
can
problem.
find you can find slopes without even doing the
The
regression.
regression.
Yeah.
Yeah. And it tells you how the slope changes day by day. It's dynamics. And it
Mm-hmm.
tells you the variation on these slopes. That is really, all these methods are just useful to identify the power law in the first place. And you see here, I made a table, for example, right, in my book. I say, okay, what are they good for? Okay, this is what the LS is good for. This is what is the quantile. Is the best way? No, because some of them have some good things and they have also bad things, all of them. But the language of a slope that identifies, I think that is really the big deal because it's more stable. It doesn't use regression and all the problem associated with regression. You can still reconstruct the main line again. Um, it's more local because changes in that variable are also associated with the cycles. It's a more abstract because people like these lines, right? For when you describe it, this is why it's still a useful way of describing the power law, but it's not really the essence. It's basically is the difference between the position of an object and the velocity of an object. The position in physics is almost pointless, right? I'm more interested in how the object is moving, how fast it's moving, is accelerating, is decelerating, where it is at any particular point. I can always reconstruct it from the velocity, you know. So
Okay. I like your analogy more about the different tests on the body. At
yes,
least from my side,
right.
I would still say we could do many different tests, but the harmonics and the sort of what's the normalized n, the normalized n finding the slope without even the regression. Those are two interesting things that I've
Yeah. In fact, if you
learned
if you have
today.
time, reproduce it. See if you find it's anything interesting in it. It's
I will, Gio, but you know what? For me, I'm a more global macro guy, interested
yeah.
in money supply, all the other stuff. So
Get
I'm
it.
going to leave the detailed stuff for you guys. But look, one more for you. I gave this presentation last week at Peter McCormick's conference in London, and I saw you made some comments because Saylor has also been talking about how we just talked about the growth rate of the power law of the slope itself.
Yep.
Slows, we're 40% now. Saylor used this magical number if it's going to 21% without, of course, saying that it's a power law. He
Yep.
continues to avoid it. Here's how I described it, and I'll show you and just quickly go through this. But I gave this slide sort of the end. I don't know if maybe I need to zoom on this one too, but let me see if I can zoom in even more. Whoops. No, that's not even working. So a little bit light lines, but basically, Jeffrey West talked about how we had the super exponential growth and we move on these faster and faster treadmills. So I tried to model that a little bit, and you can look at the growth of U.S. debt, the stock market, the gold price, Federal Reserve. That stuff was very low in 100 years ago, 200 years ago, just like with cities and everything. Or no, actually not just like with cities. The cities started higher because they're a power law. But this is so exponential growth. If you plot it, if you actually plot the growth rate, the CAGR,
Mm-hmm.
it's just a straight line. It could be higher, it could be lower, but it's a straight line. So say if it's something like 2.5, which it was in the 1800s for the stock market, U.S. federal debt, the gold price was nothing. It's just a simple average. Then you have the Federal Reserve's balance sheet added on here from 1914 to 1971, just using famous monetary dates. You get an average like 5.5%. Then you get to 7.8. Then you get to like 8.8. And what you'll notice is you get this treadmill. So each epoch we go through, we have faster growth rates, and they happen in a shorter amount of time. So that's how I tried to show super exponential growth. But this is actually low, I think, because worldwide you have inflation in other currencies more. This is just the U.S. and stock market is 12%. If you do dividends, it can be 14%, something like that. So 8% is low. So what I said is, let's say from today, this is today, let's say we jump to 20 and we just stay there and say, okay, well, this is actually what's happening with Bitcoin. So there's going to be a tension here in that we're at 40% now. We're going to hit 30% in 2031, 20% in 2041, 10% in 2070. Before I ask my question, let me just point out, Saylor using this sort of magic number of 21%, that's not at all going to happen, because you can see that the convergence rate is way. What I'm saying is it's not going to stop at that number, because it's way faster, and the power law, you know yourself, is way more powerful than just to sort of stop at a magical 21% line. So that's 21% would be somewhere around, I don't know, 2040, 2039.
Yeah.
But my question to you would be, there's a real tension here in the financial system, in that the rest of the world is moving on this sort of super exponential growth, faster and faster at shorter and shorter increments, right? So that's super exponential growth, whereas Bitcoin is doing the total opposite, right? It's growing slower. It's growing still very fast, much faster than the markets. But there's going to be an intersection. And to me, that's the interesting question. It's like, is that the singularity? Is that the Bitcoin standard? Are we going into a new financial system?
Actually, the fact, first of all, let me share. If you can, stop, and then I will share. Because I actually have a slide of Saylor. You see it?
It's coming.
Yeah. So I took this slide from Saylor. Let me make it a little bit bigger.
Yeah, zoom it in.
This was in Prague. That was his model. And here is the power law. The power law is the blue line.
Right.
And the red line is actually the median of the CAGR. And you can see they are converging. They are basically, it's a very good representation. The blue line is a representation of a real CAGR.
But he doesn't use the term power law, right?
No, at all. And then you see, as you projected, it's basically the same line, is the same projection. It's exactly the same projection. But, he's making it up. I'm pretty sure the way he explained it is an exponential with decaying rate. That is exactly what a power law is, because a power law has the same form of an exponential, but with the factor of 1 over t. If you're looking at the change in growth of an exponential, it's a constant. The exponential is the same formula for the power law, but with 1 over t, and that is the decay that you're seeing here. Is exactly the same. So I think he knows about the power law, but then he doesn't want to marry to it, and so he has this weird made up, because if you take it at face value, will be, I'm just making a guess based on what, Instead, we have a model that is, it's
all your models will be destroyed until he has his model.
Right, exactly.
Bull, bear, normal.
But so the idea is, if you're looking at, so it's basically becoming flat, almost flat, right? Yes, it's decaying, but not by much. And we will have to go all the way to 46 to get 21. That is still a big amount in comparison, even with your fast exponential growth, right?
Mine will be 2040.
2040, when they cross each other, right? When they
at 20%. They would cross each other. Actually, around that time. Yeah,
exactly.
around that time.
Because the 21% is when Yeah, they should be crossing each other.
It would be ironic if it was 21%.
Guess what? Because first of all, Bitcoin will be something on the order of $15 million, right? That will be the CAGR. That will be the market cap of almost all the real estate in the world on that order, right? We're talking about reaching market caps that are equivalent to almost the wealth in the world. Where are we going? And not just that, there are these crazy projections. You were talking about the singularity. You probably know about the technological singularity, that is this prediction by this guy Kurzweil that actually predicted the AI happening in the 20s. He has this big, huge book. He has been actually one of the biggest inspiration for making my long-term projection, because this is what he did. He has a book full of these long-term projections mostly they are exponentials.
Mostly exponential. In fact, all exponential.
Because he's talking about technology. And technology grows as exponentials. But, he was a big inspiration for me. And he says in 2045, AI will become conscious, and there will be a singularity in the sense that the pace of technology will be so fast that it will look like a spike. And then that is the end of history as we know it. So I don't know. Everything points in the direction where something big is going to happen,
But West is not talking about. He says it's possible that it could be, but his is a mathematical singularity, which is that shorter and shorter and shorter and higher and higher and higher until you're.
Right, they are the same. It's the same language.
Doesn't make sense.
Kurzweil is talking about these changes in technology. They became faster and faster and faster, where basically in a day you're going to have a change of 100 years. And that, according to his projections, is going to happen in 2045. So it's kind of interesting thing, maybe it doesn't happen, but something big, people don't realize how fast everything is happening, technology, AI, progress, where if you want to do projections in the future, more than 20 years, this is what I say all the time. It's already amazing that we can say with a certain level of certainty what Bitcoin will be in 20 years. Beyond that, it's incredible speculation. We don't have the tools, I think, to make projections beyond that, given all the things that are happening in so many different areas. But it's interesting that Bitcoin will be on the order of almost all the wealth in the world at that point.
That just so you know my position for the Scientific Bitcoin Institute. My position is that's unsatisfying, because real estate is going to keep growing. The money is going to keep growing. The Federal Reserve's balance sheet could go to $90 trillion. There's nothing stopping that technically. Mm-hmm. So those talks or those points about Bitcoin being larger than those things, I think that's possible, and it's totally possible and interesting. But to me, the key question is going to come down actually to the math. It's going to come down to either the power law, which is, as you know, sustainable, proportional, scale invariant, very beautiful. A lot of networks grow this way, cities, all the things you've done, researched. And then you have exponential, which is this sort of inherently unstable model. Yeah. And every time that we've gone through a period of instability with exponential before, you've either had a major global financial crisis or war or debt expulsion or debt jubilee. There's no really way around it, and then you reset. So I don't know if it'll be dramatic. I don't know if it'll be smooth, but they can't go together. Like they just can't. In the financial, there's nothing in the financial world that will pay a declining rate of interest. That's the key point to me. Mm-hmm. It just won't. It will not.
This is why I'm saying everything points out to that moment to be some kind of a critical moment. Because even if you say, well, okay, real estate is going up, but by factor of few, right? We're not talking about factor of order of magnitude.
Yeah, but all of that real estate has underlying fiat
Right. I
interest
get it. I get it. I
units
get it.
that they have to pay
But
in a
you see, look at what
compound
I'm saying is
exponential
that you have
function.
this thing that is extremely valuable. That is kind of equivalent of a fiat value of entire economy of a world, where is going to be at that point so serious that is going to be an alternative monetary system. And this is one of the things that I say, actually, this is when probably nation states will pay attention. When Bitcoin is $10 million, you cannot ignore it. You can't, no nation will are going to ignore a $10 million Bitcoin. Okay. And also all these other things, the pace of technology, where we're going to be with in terms of computation, all these things are converging, where some big event is going to happen. I say often that I think when Bitcoin reaches that level of market caps, the power law ends. The power law is no more, because it's like a phase transition. We're going to have
But
some
does
kind
that
of.
mean?
It means that
Sorry.
something happens where they need to take to seriously Bitcoin, and maybe a big event like hyper Bitcoinization happens. Some big nation says we're going to peg our currency to Bitcoin. It's going to happen during that time. If it is 43 versus 48, but it's going to be about 20 years from now, when Bitcoin has that kind of value that is
Yeah.
comparable with some of the you know biggest market caps that we are aware of, right? So, and even if these market caps go up because of inflation by a factor of 2 or 3, it doesn't matter. You have just to wait a couple of years more to get for Bitcoin to go there. So it's
So
going to be,
here's
you have saying that there will be some big phase transition.
yeah. What I hear though, when I hear pegging to pegging a currency to Bitcoin or a phase transition, like you say, I do hear exponential growth. I hear more
No,
fiat units being
no,
pegged
because
on a limited
if it
supply
is
of.
peg, then the exponential is no more. So it's
Why? Why is there no exponential if it's pegged? The gold was pegged and there was exponential growth.
no. I mean, what do you mean, growth in the economy or
Yeah, yeah.
growth in
I
the?
mean, if they
Oh
peg
no,
their
but there is no
fiat
problem.
currency to Bitcoin,
No, there is no
that means
problem. So
more and more.
West
That means
explains
more and more fiat units around the same literal
West
number of Bitcoin.
explains
And
that. No,
if we
no,
can't withdraw that Bitcoin, that's an exponential world of Bitcoin. By the way,
no, no,
Bitcoin holders are going to do fine in that scenario, but that to me sounds like
no,
a
no,
very
no, no.
revamped gold
In
standard.
fact, that we need to. Well, it's revamp gold standard. And during the gold standard, the economy was stable. It was no runoff exponential.
It was absolutely runoff in certain countries, in certain. It was always
That didn't
exponential,
have
Giovanni.
they didn't have the gold standard. In fact, that is one of the things that I read. I don't know if you noticed. I published another paper. I mean, I posted another paper where I made some toy models of fixed um, money supply economy, and you can show that is not exponential at all. That is actually what is exponential is, I mean, sure, the growth, the technological growth is still going up exponentially, unless again we have some big phase transition where if this singularity is a serious thing, it sounds science fiction or doesn't sound serious. People should study my book. In fact, the physics of Bitcoin, I mentioned Kurzweil as a critical thing that people should learn, because I
Mm-hmm.
think it will play a key factor. This idea of singularity, of technological singularity, will play a key factor in what is going to happen to all of us, including all the economies of the world. If you have AI, if you have agents that are as intelligent as the entire humanity, not even a single human being, but the entire humanity, anything that we have as a reference in terms of economy, etc., is gone. Doesn't apply anymore. So this is
That
why I'm saying these are the
that's
time
the key
scales
point.
where we can make some prediction. We say we are going there. These should be the values. This is where the economy, the traditional economy, is going to be. But beyond that line, beyond like 50s, 60s, I will not go there. I will not trade there because everything is moving so fast.
Yeah.
It's almost impossible to make prediction beyond 20 years at this point.
Yeah. I that's the key point there. Uh, that's a very good way to end it, I think, Gio. I agree with you. I mean, it's going to be wild in 20 years. It happens to be 20% growth of the power curve on a OLS in 2041. So right around the Kurzweil, Sornet as well had one. Jeffrey West as well. They're somewhere around late 2030s, early
Yeah,
2040s.
something big is going to happen. Yeah.
But I still, it's other than just chalking it up to AI and the singularity and all that, which I think is fine. That's one solution. There's a mathematical question that still lingers in my head, and that's you know that's exponential interest. I mean, compound interest. You cannot get around that in the economy. And if you
Right. And this is
if
why we need some kind of reset, and probably the reset will be that singularity, the technological
yeah,
singularity.
but I wonder if it would even be without that. You'd go to sort of people talk about the equity contract, right? That's possible. The sort of the all-in equity like deal where hey, I'm gonna invest in you to go study or whatever,
Right.
and I'm gonna invest in you to do this and that, and you can pay me dividends from your salary or something. There's seems to be risks inherent to those as well, but you you cannot if you grant that the power law is no more under this scenario, then I guess that's a get out of jail free card. But if you still grant that the power it's still going to do power law stuff, whether
I
it
don't think
grows in
it's going
hash
to do
rate,
power law stuff. It's going to be really a different book. It's going to be a different scenario that needs to be
yeah,
studied. That is one of the things that the Scientific Institute will study. I started, right? I did this at a certain point. I can share it with you, but I did like a little toy model where they say, okay, you have agents, we have an economy with a fixed cap supply. Um, there are different motivations of these agents, how this system will behave, and it's a stable system. It doesn't collapses and everything, so it doesn't use fiat. Because it's one of the things that many economists say. They say, oh, if you have a deflationary monetary system, or if the money is not inflationary, then everything collapses. No, it's not true. It doesn't happen. It doesn't have to happen.
but what I'm saying is, if even if it goes into a power system, and even if you're on a Bitcoin standard, using some sort of compound interest gets you back on that train, and that's the catch.
Right. We will need
It
to
doesn't
change.
matter.
We will need
It
to
doesn't matter
change. We will
if
need to change what investment is, what taking a loan is. Yeah, we will have to change all these things. Are very difficult things to even define if you have a system where money is fixed, right? It
you said it
changes.
yourself. You said it yourself. I would not trade, and I agree with you. So there's a this actually gets back to the old central banking propaganda. Is like, oh, we need to protect not only against inflation but deflation, which of course is
Right.
nonsense under their system. But that is true. If your coin will be so valuable, and then you say John
Well, for
Smith
example, in
Joker
my
down the
model,
street.
you will have to have 70, almost 80% of people keeping their coin for these things to go in a crisis system. And you will not have, because people will need to buy food, they will need to
Yeah,
pay rent, and so there is still some money in circulation. It's just that some of the most radical concept that we have about saving, taking a loan,
a risk,
a
risk.
risk, it will change. It will radically
Yeah,
change. You know,
yeah. I think you got your best get out of jail free. Just to my question is if you say that the power law will be different, or we get into this new a new time,
I
a
have
new
said of that for
phase
a long
time.
time. I have said that over a long time. I say, because people tell me, oh, what happened in 60 years? I say, no, I don't want to do prediction more than 20 years because,
Yeah,
first of all, it's very difficult to say that. But also, I always say the same thing. I say there is The market cap of Bitcoin will be equivalent to some, like basically the real estate, etc. So when you arrive to levels like that, this is when the nation states will pay attention. I always say, in fact, you can use the power law as a predictive of when, for example, Apple will invest in Bitcoin. Because if Bitcoin reaches the market cap of Apple, that is when Apple will start to pay attention to it, right? And
Apple's growing faster than 20%. It's growing 25% on a trend since
Right.
2008.
So nations, you will have to have a GDP that is equivalent to entire nation for nations to say, wow, I need to pay attention to this thing. So it's actually almost a predictive tool to when these agents will start to be involved in the network. Because I always say that it's like basically different size of agents are coming in, like an ETF. When people say, oh, ETF will have a big impact on the power law. No, they don't change the power law because it's just another agent coming in, at the right time, at the right moment.
Yeah, 100%. What I can tell you, though, is you look at the speed of this decline is not going to hang around at 21%, like Saylor says, and just converge there. It's going to go. It's going to go way down.
That is completely nonsense. I agree with that. That is completely nonsense.
Well, listen, this is what I'm thinking about, Gio. I think this is a very fascinating discussion today. Thank you. Both on the, for me, what is it? The log normalized. Explain it again. How do I quickly describe how you found the 5.8?
Slope or daily
the local slope.
Yeah. That I think is my biggest contribution so far, more than anything else, because it really goes to the core of what the power law is about. It's a dynamic process.
Yeah, the local slope and then the harmonics as well going into 2027, I think is going to be very fascinating to see.
Yeah.
Chart that over the PSR.
I will.
If you can. You're going to see something a little bit different.
Yeah.
And it's minor related.
Interesting. Yeah.
All right. Gio, thanks. If anybody wants to find anything more about the Scientific Bitcoin Institute or anything.
Yeah, we are going to have a website that will be a point of reference, where it be classes, courses, all our manifesto. We have this beautiful manifesto about what we think Bitcoin is. They can go to scientificbitcoininstitute.org. That is our website. And the book has also a website that is called the physicsofbitcoin.com. So go there because it's going to be the companion book, the companion website of the book. There is a live charts that you can go and check. And so, a lot of learning material.
Thank you, Gio, for coming on so early in the morning your time. I really appreciate it. Really enjoyed it.
My pleasure.
And all the best. Good luck with your book release. April 10th as well. People can check that out. All right, Gio. Thanks. Have a great day.
Bye.
Take care. Bye, everybody.